Hey everybody, hope you're having a great day. Today we're going to learn lesson 3.1.2, which is all about complex numbers. So if you've ever heard of I being used in math to represent a number, that's what a complex number is. That's what we're going to work on today. Okay? So working with I. Make sure you have notes or paper and pencil beside you so you can take notes and work the examples as you go. And don't forget to always let us know if you need any help. Okay, so a quick little warm up just to practice combining like terms using X because we're going to apply this later to working with the letter I in math. So do me a favor, pause your video, solve these quick problems, and then resume to check your work. Okay, so the first one, I got X plus 8. So remember when you're combining like terms and there's a plus in the middle, you just follow the operation that's stuck in front of that parentheses. So 5 plus 3 would be positive 8. And negative 2x plus 3x is positive x. And we typically write our answers in order so that you have the highest exponent first, going all the way down to the value that doesn't have x. So that's the order you normally write them in. That's called decreasing degree order. And then number 2, when you have a minus in front of parentheses, you have to distribute the minus to every value in that parentheses behind it. So it changes the sign of the 12 and it changes the sign of the x. So it becomes 2 minus 12 becomes negative 10, and 6x plus x is 7x. And then number 3, when you're multiplying two terms times two terms, you're going to multiply every value times everything. So I always start with the 5, and you distribute it to the 6 and the negative 7x. So 5 times 6 is 30. 5 times negative 7 is negative 35x. And then I work with the 4x. I do 4x times 6, which is 24x, and 4x times negative 7x, which is negative 28x squared. And then you rearrange and combine any like terms that you can. So the negative 28x squared goes first, then negative 35 plus 24x is negative 11x, and then plus 30 just tags along at the end. Okay, so your sabbat for today is to work with complex numbers. Specifically, we're going to add, subtract, multiply, divide, and do some operations with square roots of negative numbers. Okay, so what is a complex number and how does that differ from an imaginary number? So we use the word complex number specifically to represent something, and then we use imaginary to represent something. So let's talk about it. So some quadratic equations, and a quadratic is an x squared equation. So anything that the highest exponent on an x is a 2 is called a quadratic. And we'll go over that a good bit in the next lesson, so 3.2. So some quadratic equations have no real solution. So remember we've talked about real numbers before. They're rational, irrational, natural, integer, and whole numbers. Those are your real numbers. But there is a such thing as an imaginary number. So if you have a quadratic that doesn't have a real number solution, you can utilize the imaginary number system or the complex number system. So for example, if I give you this equation x squared equals negative 1, it doesn't have a real solution because there's not a number in the world that if you square it, that you'll get a negative number. Because remember, when you square a number, the sign gets multiplied also. And the negative times a negative will always be a positive. So there is no real solution for that equation because x squared can't produce a negative. So to overcome this, the mathematicians way back in history created something and expanded their number system to something called the imaginary unit. In math, anytime you see the word unit, that is a 4-letter word for the number 1. Okay, so when I say imaginary unit I, that means 1I. Okay, and every time we write I write it kind of like it has a tail in cursive, so that it doesn't look like a 1 with an accidental dot on top. So you'll never see me write I this way. You'll always see it as in cursive, okay? All right, so we'll talk a little bit more about it on the next slide, but notice that every time we've talked about real numbers, we use this funky R. Well, I belongs in the complex number system, and so it's a C like this. So this stands for complex. And remember, this R stands for real numbers when we're talking about sets of numbers. Okay, so complex numbers and imaginary numbers. The imaginary unit has a definition where I is equal to the square root of negative 1. So anytime you're working with a problem and you're solving it and you end up square rooting a negative, you're going to introduce I. And I will promise I'll show you how in a couple examples. But you need to memorize this, learn this, make sure it's committed to your memory that I stands for the square root of -1. And following that, if I were to square I would get I squared. And remember the property that if I square a square root, that cancels and you're left with just the radicand, or -1. Okay, so the definition of a complex number is it's a set of all numbers that you write in this form, a plus bi, where a and b stand for numbers, but I will always be the square root of -1. But we write it as I, not the square root of -1. So anytime you write a number as a complex number, it will be a plus bi. So you'll have a real number part, that will be a, and then you'll have a complex part or an imaginary part, which is bi. And it has an order. You always have to write the real number first, then the imaginary second. So if I say an imaginary number, I'm only talking about I. If I say a complex number, I'm talking about a problem where I can write it in this form, where it has a real number part and an imaginary part. So the cool thing we can do with our I is we can work with it. So mathematicians said, just because I get the square root of -1 doesn't mean I have to stop there. We can keep working. So we have operations with the imaginary number and complex numbers that we can do. So anytime you have a number written in the form a plus bi, it can be added, subtracted, multiplied, just like if it were a plus bx. So just like in your warm-up, if you had 2 plus 3x plus 8 plus 2x, you would add the numbers and you would add the x terms. You would combine like terms. So we can work with I the same way. So we can add, subtract, and multiply them very similarly. There's one little hiccup with multiplying, but I'll show you how that differs from real numbers in just a second. But just know that most of the time when you're working with I, you're going to treat it just like it's x, honestly. Okay, so let's practice and see how you do. What I want you to do is just add and subtract these two binomials. Treat I like it's x. But then when you're writing your answer, it always should be of the form a plus bi. Or it could be minus if your b is negative. But your real number goes first and your I goes second. And you should never have any exponents on your i's. Okay, so pause the video and see what you can do with those. And then press resume to finish or check your work. Okay, so these are actually the problems from your warm-up where I replaced I with X or X with I. And so you have the same thing, except for in the previous problem, we would have, sorry, that's a plus right there. So it should be 8 plus I. When we had X, we wrote the X before the constant. But when it's in terms of I, the I always goes after, okay? So this is a complex number. You have a real number 8 and you have an imaginary number I, okay? I know that you're thinking probably, I is a letter, Miss Rogers. But in this case, it's a number because it represents the square root of -1. Okay, and then for B, it's the same exact thing. On the warm-up, you got 7x minus 10. Here we have -10 plus 7i. Because we're dealing with I, it has to go second. So when we want to multiply complex numbers, we work with them just like they're x, except for one stipulation is that you cannot have any powers of I. Okay, no powers of I are allowed. You must convert them. So I will show you what that means in just a second, but pay attention that your answer, no matter what, will always be written in this order. So we're going to work with it just like as if it was x. So we'll multiply 7i times 2 and 7i times -9i. So that's the distributive property. So 7 times 2 is 14i. And then 7i times 9i would be -63i squared. So remember, if I is equal to the square root of -1, then I squared is equal to just -1. So this is how you convert it. Anytime you have I squared, you're going to rewrite that as a -1. Okay, and then you simplify that. So we do order of operations. -63 times -1 is going to be positive 63. And then 14 was positive. So I'm doing order of operations, but also rearranging it so that it's in a plus bi form at the same time, and that's okay. But if you didn't want to do 2 steps in one, you can simplify it and then rearrange it. Just make sure that the number, if it's positive, it should have a plus sign in front of it when you rearrange it. All right, so for b, we're going to multiply. So we're going to do 5 times 6 is 30. 5 times negative 7 is negative 35i. And then 4i times 6 will be positive 24i. And then 4i times negative 7i will be negative 28i squared. Does this look familiar? This was one of your warm-up problems, except for we used x in those. So now we're going to simplify where we can. So you have 30 minus 11i minus 28, but anytime you have I squared, you replace it with negative 1. So that's going to become positive 28, and you'll be combining that with 30. So 30 plus 28 is 58, then minus 11i will be your final answer. So it follows all the operations just like as if you were working with a variable x, except for you're not allowed to have any exponents on your I. You always have to convert it so you have a real number and then an I part or imaginary part. Okay? So we've added, we've subtracted, and we've multiplied with complex numbers already. And now the next part though is you have to understand what a conjugate of a complex number is prior to doing the division operation. So we're going to go through the definition of a complex conjugate. I can't say it today. Okay, so the conjugate of a complex number. So if I have a complex number of the form a plus bi, its complex conjugate is a minus bi. So the way to find a conjugate is you're just changing the sign of your I term. Okay, and the really cool thing is when you go to multiply a number or a complex number and its conjugate, you should always end up with a real number. You should not have I anymore. So we're going to prove it, okay? So we're going to prove it by multiplying a plus bi times a minus bi. So we're going to do a times a is a squared. A times negative bi is negative abi. Then we're going to multiply bi times a, so it'll be positive abi. And then minus, so when you do positive times negative, you get a negative. B times b is b squared. And I times I is I squared. Okay, so the cool thing is abi and negative abi cancel. So you're left with a squared minus b squared times negative 1, because I squared is negative 1. So that becomes a squared plus b squared. So notice there's no more i's, and that's how it works. And the reason we like the conjugate is because when we get to division, you're not allowed to have I in the denominator. So the way we adjust for that is we multiply the top and the bottom of your fraction by the conjugate of the denominator. And that cancels out your I for you. Okay? So the definition of a complex conjugate is it is a plus bi. Its complex conjugate would be a minus bi. You change the sign of the I term. Okay, so now we're going to move back to operations. So we added, we subtracted, we multiplied, now we're going to divide. But division with complex numbers is not necessarily long division like you're probably thinking. Our division of complex numbers will basically be simplifying so that it's written in the proper format. So the goal of complex number division is to obtain a real number in the denominator. So just like I told you, you're not allowed to have a power or exponent on your I. You're not allowed to have I in the denominator. So the way we do this, there's your steps. You're going to multiply the numerator and denominator of a complex number. And we just say complex number quotient. That just means complex number fraction. So we multiply the top and the bottom of the fraction by the conjugate of the denominator so that we no longer have I in the bottom. And feel free to pause it so you can write this down if I go too fast. So here's a quick example. We're taking this fraction, 5 plus 4i divided by 4 minus I. We're not going to do long division with this. We're going to identify the conjugate of the denominator. Okay, so first you have to be able to identify the conjugate of the denominator, then you're going to multiply the top and the bottom by that. Okay, so you take your denominator, which is 4 minus I. You rewrite it, but you change the sign of the I term. Okay, so that's the first step, is to identify what is the conjugate of the denominator. And it's the same thing as you see, except for you change the sign of the I term. Now, just like if you were taking a fraction, so I'll do a little bit of fraction recall over here on the side. Remember, if I were doing 2 divided by 4 and I wanted to reduce that, I would divide the top by 2 and I would multiply or divide the bottom by 2. That's the identity property of 1. You can multiply or divide any number by a value of 1 and it doesn't change it. And that's how you get 1/2 as an equivalent fraction. So you're allowed to do that with division and with multiplication. So we're going to multiply the top and the bottom of this fraction by the conjugate of the denominator. Hang on, I wrote it wrong, sorry. There you go, 4 plus I. And I like to put in parentheses just to help, focus my attention of what I'm actually doing. So if you multiply a fraction by an equivalent of 1, it doesn't change its value. It's just like getting a common denominator. So then the result will leave you with a real number in the denominator, and that's the goal. So what we're going to do is we're going to multiply the top, and then we'll multiply the bottom. So when you multiply fractions, you multiply straight across. So we will distribute here. So 4 times 5 is 20. 5 times I is 5I. And then 4I times 4 is 16I. And then 4I times I is 4I squared. And that's your numerator. So guys, just for my sanity, that when I'm doing this, I figure out all of my numerator steps and then I go back and do the denominator. I don't like to do 2 things at once because you can lose track very quickly. So I'm going to work on just the numerator. So this becomes 20 plus 21I plus 4 times negative 1. So that'll give you a negative 4 when you multiply it. So then 20 minus 4 is 16 plus 21I. So that's all of your numerator. And then just to save myself some heartache, I change colors and I work with just a denominator. So now 4 times 4 is 16. 4 times I is 4I. Negative I times 4 is negative 4I. And then I times I here would be negative I squared. So the i's cancel, and you're left with 16 minus negative 1, which would be 16 plus 1, right? So that'd be over 17. So then remember that you have to write it of the form a plus bi. So this is not in proper form until we split the fraction up. So this becomes 16 over 17 plus 21 over 17i. So this is your a, this is your b, and this is your I. So that's how you split it up into proper notation when you have a fraction. But notice that there's no more i's in the denominator. Okay, so that's how you divide. You multiply the top and the bottom by the conjugate of the denominator. And so over time, you'll see some strategies that could save you some time. But the first time we're doing it, we're going to go through all the steps. And guys, please don't hesitate to reach out and email if you have any questions. All right, so the very last thing we're going to go over today is the one thing that doesn't work the same way as if you're working with real numbers. So when we were working with square roots of negative numbers, we have to pull out the imaginary part. We have to simplify a radical before we can do anything else with it. So we're going to recall from last week's lesson that when we simplify our fractions, we pull out the perfect square part. But now that they're negative, we also want to pull out the negative part. So I'm going to have, to my factor tree, I'm going to have 3 branches now. I want to write them a little prettier. Okay, so you're going to think about your list that we made. And you're going to remember that 9 is the biggest perfect square that goes into 27. So it's square root of 9. Then the leftover to get to 27 is 9 times the square root of 3. And then, because it's negative, you have to pull out the negative 1 all by itself. So then you can go ahead and simplify this. We know that square root of 9 is 3. Square root of 3 is my leftover. And then the square root of negative 1 is I. Okay? Normally, we would put everything that's out of the radical, we would put in front. But because it's I, you have to put all of your real stuff first, and then your I. So this one gets written this way instead. Okay, and then we'll go through and simplify this one the same way. So we have the square root of 16 times the square root of 3 times the square root of negative 1. So that will give you 4 root 3 I. And now we have like terms that we can work with. So root 3I and root 3I are the terms that have to match. And then the coefficient is the 4 and the 3. So now you're just going to do 3 plus 4 is 7 plus root 3I. And that is, no, sorry, not 7 plus, 7 times. 7 times root 3I. I'm sorry, y'all. Okay, so that is simplifying. This is a simplified imaginary number. This is not a complex number. If I were to ask you to write it as a complex number, you have to have a real number part. And that real number part doesn't exist, so we would put 0 in its place. But that's only if I asked you to write it as a complex number. If you don't have a real number part, you put 0 there. But the directions here were just to simplify. So this is fine for this problem, okay? All right, so just pay attention that anytime you have the square root of anything negative, you pull out the negative as the square root of negative 1, which is I, and then you work with the number as if it were positive. You just have I beside it. Okay, so the operations with these square roots of negative numbers. Again, you have to simplify the radical before you do anything else with it. So if you're looking at A and you're thinking, oh, I remember that property that said the square root of m times the square root of n is equal to mn, both together under the radical. This property does not work or is not allowed with complex numbers. Okay, so that's that fancy C. I was just writing it, so I ran out of room. But I'll write it with complex numbers. Okay, so you cannot do this. You cannot multiply the numbers under the radical when there's negatives there. And here's why, okay? If I multiply 3 times 12, that will give me 36. And the square root of 36 is 6. If I multiply negative 3 times negative 12, you get a positive 36, which does not account for I. So it eliminates your signs if you follow that process. So this is why we have to rewrite this as root 3I. We pull out the negative, and then we'll rewrite this as root 4 times root 3 times the negative 1. So we'll pull out the negative. Let me backtrack so I can show you my work on that. I'm sorry. This is root 3 times root negative 1. So this is root 3I, and this will be 2 root 3I. Okay, and then now you're allowed to multiply them. So remember, when they're stuck together, it just means multiply. So when you multiply these, you're going to multiply the coefficients. And in this case, there's not a number in front of that first root 3, so it's just a 1. So 2 times 1 is 2. Root 3 times root 3 is root 9. And then I times I is I squared. Well, root 9 is just 3. So that becomes 2 times 3 times negative 1, so that's negative 6 in the end. So this is the reason for that. If you don't pull out that negative first as I and then solve the problem, you're going to eliminate your negative. You're going to have the wrong sign in your final answer. So pay attention to this very carefully. You have to simplify the radicals first. When the radicand, that's the number under the radical, is negative. If you don't do that, you'll get the wrong answer, the wrong sign, okay? All right, so then let's look at B. Again, we're going to pull out the negatives first. So if you guys want to pause it, because I think you could do B without me. So why don't you pause it, try B by yourself, and then resume to check your answer. Okay, so for B, I wanted to make sure you saw the directions before we simplify our answer all the way. So the directions on part B says write the complex number in standard form. So remember that standard form of a complex number is your real number part plus your imaginary part. So if I say write it as complex number in standard form, you have to have a real number part. And in this case, there was no real number part, so we put 0 in its place. So the final answer for part C is 0 plus root 3i. Okay, so if you wrote just root 3i, you got it correct, but it's not in the right form, so we just have to convert it that way. All right, so then part C, we're going to rewrite as -1 times root -3 times itself. Because remember, when you square a binomial, it means multiply it times itself. Okay, and so before we simplify any further or try to multiply these out, we have to simplify our radical and pull out the I first. So this becomes -1 plus root 3i times -1 plus root 3i. And now you can multiply the two binomials together. So -1 times -1 is +1. -1 times root 3i is negative root 3i. And that gives you another negative root 3i. And then remember, when we multiply root 3 times root 3, we just get 3. And I times I is I squared. So combine like terms and then replace I squared with -1. So you have 1 minus 2 root 3i plus 3 times -1, which is -3. And 1 minus 3 is -2. So it's -2 minus 2 root 3i. Okay, guys, so that's it for 3.1.2. Now you just get to practice. So please make sure you're working these problems on your own and checking your answers with the solutions that are posted for you. So today at page 159, problem number 1, we're actually going to do together because the directions are kind of misleading. So after I go over all the homework, we're going to sit down and actually do number 1 together. So you have number 1, which we'll do, and then you're going to go through and do 7 through 10, 13, 14, 19, 21, 29, 33, 35, 37, and 41 on this page. And then you have 2 division problems to do. So don't forget the steps for division is to multiply the top and the bottom by the conjugate of the denominator. Okay, so we're going to go through number 1. I just want you to notice the patterns after we go through and list all these out. So the directions for number 1 says write out the first 16 positive integers of I. So we're going to start with I squared, I cubed, I to the 4th, and we're going to go all the way through to I to the 16th and calculate those out. And then see if we see any patterns at all. Okay, so we'll start with I, we know is square root of -1. We just write that as I most of the time. Then I squared we did earlier. Whenever you square a radical, they cancel out, and you're left with a radicand. So that's just -1. Now, if we go to cube it, you're actually going to say I cubed is the same thing as the square root of -1 cubed. Okay, so if I do that, I get the same thing as the square root of -1 squared times the square root of -1. So that gives you -1 times the square root of -1. Well, the square root of -1 we have determined is I. So anytime that appears in our work, we'll just rewrite that as I. So -1 times I would be -I. Okay, and then I to the 4th is the same thing as I squared squared. And I squared we determined was -1, so -1 squared would be +1. Okay, so in the directions it says write each as I, -I, 1, or -1. So notice that we started with I, then the next one is -1, then we have -I, then positive 1. Okay, so we're going to keep this pattern going and do I to the 5th, I to the 6th, I to the 7th, and I to the 8th. So the same manner. So you take the previous one and multiply it by I. That is the easiest way to get through this. So the previous one is I to the 4th, which is just 1, times I. Sorry. So 1 times I is just I. Okay, so then we take I to the 5th, which is I, and multiply it by I again. And that's the same thing as I squared. And we know I squared is negative 1. So I to the 7th, we'll take our negative 1 and multiply it by I. So the previous one times I gets you to the next one. So that's negative I. So then we have negative I times I is negative I squared, which is positive 1. Okay, so I hope that you're noticing a pattern. So we have I, negative 1, negative I, and 1. So if you look at this pattern, it's repeating after every fourth exponent. So if I do I to the 9th, I to the 10th, I to the 11th, and I to the 12th, we should get I, negative 1, negative I, and 1. And then I to the 13th, I to the 14th, I to the 15th, and I to the 16th will give you I, negative 1, negative I, and positive 1 again. Okay, so I'm going to leave you with this question to do for your homework, is to tell me what patterns do you notice through this? And then could you continue this to like out of the 100? How would you do that? So that's for you to kind of come up with your explanation, but I wanted to help you through the I to the 16th part. Okay, so don't forget, join the Zooms if you have any questions, or email Ms. Gatlin or myself, and I'll be happy to help you with any of these questions that you have. Have a great day.